In this video, we're going to see several examples of induction or proof by induction. So we're going to go through and prove the following four facts. So we'll show if n is a non-negative integer, then 5 divides n to the fifth minus n. And if n is an integer and n is greater than or equal to 0, then the sum from I equals 0 to n of I times I factorial is equal to n plus 1 factorial minus 1. And then we'll also see proofs for number 3 and 4, so I'm just going to show you what those proofs would look like, and then we'll talk through where those different pieces come from and why they're important. So let's start with this one. If n is a non-negative integer, then 5 divides n to the fifth minus n. So again, because I'm trying to prove this for all integers, or in this case non-negative integers n, I can use induction. So I'm going to start with my base case. So maybe at the top we'll put in proof, and we'll tell the reader that we're going to use induction here. So we'll say we'll proceed by induction, and then label our base case. Because I'm starting or wanting to prove this for all non-negative integers, the first one is when n equals 0. So my base case is going to be when n equals 0. So I'll say let n equals 0. Then I'll think about having to prove, so what I need to prove is that 5 divides n to the fifth minus n. So again, I can't just write 5 divides that. I actually have to think about why it's true. So we can note that n to the fifth minus n is equal to 0. And now I can say 5 divides 0, and I should put it in a descriptor, since we need to show that 5 times something is equal to 0, and we know that 5 times 0 is equal to 0. All right, A divides B if B is equal to something times A, where that n is an integer. So 0 counts. So I have that the 0 is equal to the 5 times something. Okay, so our base case holds. So now we can go on to our inductive step. So for my inductive step, I'm going to assume that this statement holds for some k. So assume for some fixed but arbitrary k and n, 5 divides k to the fifth minus k. And now I want to put down what I want to show here, just so that we can keep in mind where we're working. We want to show that 5 divides k plus 1 to the fifth minus k plus 1. So I'm going to assume it's true for some k and prove that it's true for k plus 1. So let's think about how we can go about proving that. Right? I'm trying to work with this quantity here. I'm trying to show that 5 divides k plus 1 to the fifth minus k plus 1. I can't just start with that statement because I don't know that it's true. So instead, I'm just going to start with this k plus 1 to the fifth minus k plus 1. And I'm going to say for sure what I know it's equal to. So we see that k plus 1 to the fifth minus k plus 1. I'm just going to go ahead and multiply that all out. For this fifth power, I'm going to use sort of a binomial expansion. So I have k to the fifth plus 5, k to the fourth plus 10, k cubed plus 10, k squared plus 5k plus 1. Right, so I'm getting these coefficients from the Pascal's triangle. So I went to that fifth row. Of Pascal's triangle, and that gave me the coefficients for my binomial expansion. All right, so that was just k plus 1 to the fifth minus k, distribute that minus 1. So my 1's cancel, and I'm just left with k to the fifth plus 5k to the fourth plus 10k cubed plus 10k squared plus 4k. Now I know that 5 divides k to the 5th minus k. So I want to try to change my k to the 5th and my k terms into a k to the 5th minus k. So I note that I can take this 4k. 5s are good because those are divisible by 5, so I can write it as a 5k minus a k. So maybe I should have actually left it in the way that it was originally, but that's okay. We sort of noticed that later. So that's going to be k to the 5th. And let's go ahead, well, I'll just rewrite this line for here. We could maybe skip some of these steps. And you could always rewrite this a little bit better after you see all of the pieces coming together. So now I'm going to write this as k to the 5th minus k plus 5 times a bunch of other stuff. Oops, I got to factor the 5 out. So we'll put the 2 out for there we go, plus k. I don't know why I wrote a 5 here. I meant to write a k. All right, so now I know that 5 divides this. And maybe we can go back and put in a little extra line here. So k to the 5th minus k is equal to 5n for some n. Where would he used n in the problem to mean something else? That's what the variable used before up here. So I'm going to use m instead, where m is z. So then this we said was equal to 5m plus 5k to the 4th plus 2k cubed plus k. So that's just 5 times m plus k to the 4th plus 2k cubed plus k. Therefore, I showed that this quantity is equal to 5 times some integer. So 5 divides k plus 1 to the 5th minus k plus 1. That's what we wanted to show, so we'll say as needed. And now we'll just write our conclusion sentence. Thus, by induction, we've shown that for all n in Z greater than 0, non-negative integers, 5 divides n to the 5th minus n. Okay, take a second, read over this proof, see if you can understand where all of the pieces come from. You might want to think about rewriting this step, see if you can get rid of some of those steps to make it a little bit more clear and concise. And then we'll go on to the next one. Next, let's look at the proof of the following statement. If n is an integer and n is greater than or equal to 0, then the sum from I equals 0 to n of I times I factorial is equal to n plus 1 factorial minus 1. So before we get into the proof of this, let's just do a little bit of background work here so we can get a feel for what this is saying. So I'm looking at this quantity, the sum from I equals 0 to n of I times I factorial. So when I equals 0, that's 0 times 0 factorial, plus 1 times 1 factorial, plus 2 times 2 factorial, plus 3 times 3 factorial, and so forth. And I go up until I get to n times n factorial. And it says that when I add that up, I should get n plus 1 factorial minus 1. So this is just 0. These two together is 0 plus 1, so that's just 1. And that should be 2 factorial minus 1. Okay, that checks out. If I do the first 3 here, I get that 1 plus 2 factorial is 2 times another 2 is, 2 times 2 is 4. So 1 plus 4 is 5, and that should be 3 factorial minus 1. 3 factorial is 6, minus 1 is 5. Okay, that checks out as well. Now I'm just going to add on this next term. So I had at 5 plus 3 times 6. So 5 and 18 is 23. And that should be 6 factorial minus 1. 6 factorial is 24. Okay, so I'm going to feel that this is looking correct. I always like to kind of have an idea of what this looks like before we start our proof, just so we can kind of know what's going on here. All right, so now I'm going to actually go ahead and start this proof. Give us some space here. Again, I'm trying to prove something is true for the set of non-negative integers, so I can use induction. So we'll say we'll proceed by induction. Now for my base case, we look at the smallest integer we're trying to say that this is true for. It says n is greater than or equal to 0. So I can let n equal 0. Then here I'm trying to show two things are equal. So remember, we can't just write down that they're equal. We have to actually look at those two sides separately and then compare them to each other. So then we can say the left-hand side, the sum from I equals 0 to 0 of I times I factorial is equal to 0 times 0 factorial is equal to 0. And then on that right-hand side, we get that 0 plus 1 factorial minus 1 is equal to 1 factorial minus 1 is equal to 0. So both sides are equal. Right, which means that the sum from I equals 0 to 0 of I times I factorial is equal to 0 plus 1 factorial minus 1, which is what we wanted to show for that base case. Okay, so now we can move on to our inductive step. In our inductive step, we're going to assume, I'm going to switch out my letters, so I'm going to assume I equals 0 to k of I times I factorial is equal to k plus 1 factorial minus 1. So I'm just assuming p sub k is true, and then I want to show, and I don't need to include this in my proof, but I can if I want. I want to show that the sum of I equals 0 to k plus 1 of I times I factorial is equal to, my k becomes a k plus 1, and then we already have that other plus 1, so that's actually a k plus 2 factorial minus 1. So here, let me go ahead and make that an I factorial, make it a little more clear. Now this statement here is what we want to show. It's not something I know already, so I can't work with both sides of that equality. I can only work with one side because I don't know that it's true yet. So that's what we're going to do. We're going to start with this first side here. I equals 0 to k plus 1 of I times I factorial. And we're going to say what that's definitely equal to. Right, so maybe you could put some sort of word in here now, and that would probably be on the next line. This, I know something about the sum up to k. So here, I want to just pull off that last term. So instead of stopping at k plus 1, I'm going to stop at k. So then I can use my inductive hypothesis. But then I need to add on that k plus first term, which is k plus 1 times k plus 1 factorial. Now, by my inductive hypothesis, I know that this is equal to k plus 1 factorial minus 1. And that still is adding on a k plus 1 times a k plus 1 factorial. And that was by my inductive hypothesis. So that's what I was able to use here. So we can label that at the end of the line so we know how we did that. Now, I know in the back of my mind that I'm trying to go to this k plus 2 factorial minus 1. So this minus 1 I have here is sort of good. I want to have a minus 1 at the end. So maybe I can just kind of pull that out over here. And then what's left, I notice that both of those have a k plus 1 factorial. So I'm going to factor that k plus 1 factorial out. When I factor it out of this term here, I'm left with 1. And when I factor of this term over here, I am left with just a k plus 1. Now, k plus 1 is k plus 2, and k plus 2 times k plus 1 factorial is k plus 2 factorial. So all those together become k plus 2 factorial, and I still have that minus 1 out there, and that's what I wanted to show. So I'll say as needed. Now we can put our concluding sentence. Thus, by induction, we can conclude that if n is an integer and n is greater than or equal to 0, then the sum, okay, I equals 0 to n, I times I factorial, is in fact equal to n plus 1 factorial minus 1. For this question, I've presented the proof in the book, and I just kind of want to go through and talk about some of the different pieces in that proof. And we can kind of compare them to the things that we've written so far. So we can kind of compare the book style to my style to see that there's a lot of things in common here. Okay, so what do we have? We're trying to show that the inequality 2 to the n is less than or equal to 2 to the n plus 1 minus 2 to the n minus 1 holds for each n. So that's the statement that we're trying to prove. And again, we start out here with a introductory sentence where we say that we're going to use induction. So we say, okay, we're going to prove this doing induction. Now they didn't label this step 1 as the base case. That's usually what I label as the base case. But they are going to go ahead and do that base case here. So here I'm trying to show that this works for all natural numbers n. So we start with n equals 1. Now they wrote what I would not do. I would be mad at you if you did this. They said, okay, well, the statement is this, and that simplifies to this, which is obviously true. That's okay because they said the statement is instead of implying that the original statement was true. But I think it would be better to just say what each of the sides simplified to first, and to then say that that's a true statement. But as long as you don't say anything that's false, then it's okay. Okay, now we're moving on. So they're saying k is some fixed but arbitrary integer greater than 1. And they're going to show that 2 to the k is less than or equal to 2 to the k plus 1 minus 1, or 2 to the k plus 1 minus 2 to the k minus 1 minus 1, implies the same statement where I've put in a k plus 1 instead of a k. Right, so I'm trying to show this implication for my inductive step here. I'm assuming it holds for that k. It's my inductive hypothesis. And now, because I don't know anything about this side here, what they're doing is they're starting with that entire true inequality. So they're taking that inductive hypothesis and they're starting that as their inequality here. For inequality ones, this is often what we're going to do. Because we can be able to say what we know for sure that that inequality holds. Right? I can't really work with my other inequality that I'm trying to show because I don't know that that's true yet. Okay, so now I think to myself, how do I get this inequality here? How do I get this to look like the thing I'm trying to show? And one thing I notice is that I need to get an extra copy of 2 on that side. So that's the first thing that they do, is they multiply both sides by 2. And then they expand this out. And they know that they're trying to get to a minus 1 over here. So here, they see that they have a minus 2, but they need to make it to a minus 1. So they actually just added 1 to the bigger side. So let's think about if we can do that. Right, if I have that x is less than or equal to y, what they did is they just added 1 to only one side of this equation. So they have x is less than or equal to y plus 1 now. So we have to think to ourselves, is that true? Well, really, we know that y is less than or equal to y plus 1, and x is less than or equal to y. So really, by transitivity, then, x is less than or equal to y plus 1. So we can do that sort of thing. So they added that plus 1 here so that they could get to a minus 1 in the end, because that's what it looked like in the thing that they were trying to show. And then they just wanted to make the powers look right? K plus 1 minus 1 is the same as k plus 2, so just rewrote it a little bit more clearly. And then k plus 1 minus 1 is the same as k, so then again they rewrote that one out. So they made it look like just like that inductive hypothesis. So finally they have this concluding sentence: it follows by induction that this is true for each n. So that's another way that you could write out these inductive proofs, and some sort of things that we can do with inequalities when we have those inequalities in our proofs. Let's go through one more proof together here. So here we have, if n is a natural number, then 1 plus x to the n is greater than or equal to 1 plus nx for all x in R, with x greater than negative 1. So here, right, I have two different things going on. I've got this n, which is a natural number, and I've got this x, which is a real number. I can't use induction to prove things for the set of all real numbers. I can only use n to prove things for the set of all natural numbers. So I'm going to do a mathematical induction proof. I'm going to induct on n. So I need to let this x be some fixed but arbitrary real number greater than 1. So we're going to induct here on n. So again, we have our introductory sentence. Proceed by induction. Tell the reader what we're going to do. For the basis step, or that's the base case, we know that the first natural number here is 1. So I'm going to start with n equals 1. We're going to look at the statement. Again, I would say what each side looks like individually. So I get 1 plus x to the 1 is equal to just 1 plus x. And then 1 plus nx is equal to just 1 plus x. And then I would say those are equal, instead of plugging things into this inequality that we don't know. Right? And they said basically the same thing. They just wrote out the inequality. But here we have to be very clear that this isn't an inequality that we know yet. So they said the statement is this. They didn't say that that statement was true. So the wording there is very careful. Okay, so this is true because both sides equal 1 plus x. Great. So now we're going to move on to our inductive step here. So what do we notice in the inductive step? We're going to assume for some k plus 1, for some k greater than or equal to 1, that the statement is true. And we're assuming it's true for all x with x greater than or equal to 1. Right, so I'm not inducting on x. I have to assume that my thing is true for all x, and then we'll prove it for all x. So again, they tell us what we're going to look to try to prove, just so we know where we're heading. That's something that is not true yet, so I can't work both sides of that inequality because I don't know that it's true. And the other thing they say is that 1 plus x is positive because x is greater than negative 1. So we can multiply both sides of the inequality by 1 plus x without changing the direction. So then they're starting here with this statement that they know for sure is true. So they're starting with this known statement. So I'll put that in green because it's known. They're not starting with their unknown statement. So they're starting with this known statement. You can't start with unknown statements. And now they're multiplying both sides by 1 plus x because that's a positive quantity. They said you could do that. Simplifying down what this side is definitely equal to. Multiplying this side out. Now they knew that they wanted that to look like 1 plus k plus 1 times x. So they kept the 1 outside. And then they factored an x out of this to see that k plus 1 times x. And then they have the kx squared here. But now they said, okay, I'm trying to get it down to just this. but this is a greater than sign, so this quantity is greater than 1 plus k plus 1 times x, because this kx squared is positive. So removing it from that right-hand side only makes the statement smaller, so we do get this thing as we need it. And I think it would be good to include a final statement here, so we can say, thus, by induction. Sometimes you'll see that people say, by PMI, which is the principle of mathematical induction. It's the really fancy way of thinking about it. So that's by induction, blah, 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 conclusion. So you can add that if you want, but you don't have to, because they said up here exactly what we needed to prove. So when they got there, they knew they were done. So for our discussion question, I want you to go ahead and try to find one other inductive proof. So you can look in the book, but it would be better if you went and just searched online and just found an inductive proof of something. And then I really want us to kind of compare that to what we've seen so far in these inductive proofs to see what they have in common, what differences they have. So I encourage you to go out, try to find your own induction proof. This is one of the times where you can actually search the internet for a proof. Screenshot that, and we'll put that into our Jamboard slides and talk about some different examples of these induction proofs in class.